Hello everyone, you should have this note sheet in front of you following along as we walk through a few examples of some applications of logarithms. Some of these you've already seen earlier in this chapter, so I'm actually going to skip to the last two examples that you've seen, and these deal with the compounding money continuously, remember using the A equals PE to the RT, versus compounding money so many times a year, n times a year, where we use that more complicated formula. So remember, these will be given to you. However, you do need to know when to use them, as well as what all of these variables mean and how to plug in your information. So I've already started this one, but assume $100 is deposited into a savings account and interest rate is 6%, compounded continuously. When will the money be double the original amount? So remember, P is 100. A is double the amount, so 200. Your interest rate will be changed to that decimal, which will be 0.06, and we're solving for T. So we go through our steps of solving the exponential equations. Remember to divide by the 100 first, and then to solve the exponential equation with a base E, remember to natural log both sides, or you can change to logarithmic form. Either way, you'll get natural log of 2 equals 0.06t, and then divide both sides by 0.06. So when plugging this into your calculator, you should get 11.552 years. And remember to always keep all of your answers accurate to 3 decimal places. Okay, versus number 7, when we read through this, it's kind of the same setup. We're assuming we are depositing $100 at the same interest rate, but now I'm not continuously compounding my interest. I'm compounding 12 times a year. So when you see that, you're using the bigger formula. And when will the money be doubled the original amount? So once again, P is 100. My amount that I want is 200, doubled that. And we plug in all of the information here. The R is the 0.06, 12 times a year, and then 12 times T. Once again, I'm solving for T. Since T is the exponent, we solve the exponential equation by dividing out by the 100 first. Very important that you remember that step. That seems to be a typical error in solving for these. And I'm plugged this in already. 1 plus 0.06 divided by 12 ends up being 1.005 raised to the 12t. Once you get that done, we're going to log or natural log both sides. I will natural log. We've got natural log of 2 equals, and we can bring down the 12t in front. So we've got 12t, natural log of 1.005. And since we're solving for t, all we need to do is divide both sides. You could do it in 2 steps, but I'm just going to do it all in one. Divide both sides by 12 and natural log of 1.005. Be careful, though, if you are plugging this into your calculator, to appropriately use parentheses telling your calculator to divide by both of those, or divide by each individually to be safe. I would actually practice on your calculator and be sure you get the correct answer, which is 11.581 years. Okay. Not much of a difference you can see from number 6, but when you compound interest continuously, you will have the most. Okay, let's look at some new examples of exponential models. So, and actually this one's not new as well. The next ones will be, but we have this a b to the x that's used for, we call it assets or equipment, but basically the keywords you're looking for is something growing at a fixed rate. So we'll usually have these words of appreciation or depreciation. And these were the ones in integrated 1 when you would change this 12% per year to a multiplier, and that's all that this formula is telling you right here, that if something is appreciating, you take the 1 plus the interest rate, or 1 minus the interest rate if something's depreciating. So you can either plug into these formulas, which we'll give you, or you can do it intuitively like the IM1 way. Okay, so I'll show you. $40,000 car depreciates at a constant rate of 12% per year. So in IM1, you just said, oh, depreciating, we do 100 minus 12, which is 88%. So remember, my multiplier was 0.88. Well, that will be given to you if you just plug in 1 minus 0.12. You can directly plug into that as well, just using the formula. So we want to know in how many years will the car be worth $12,000. So $12,000 will be our final amount. We're starting with $40,000. And our multiplier is 0.88 raised to the x. Okay. So we've got our A, our initial amount, our Y, final amount, our multiplier, 1 minus 12%, or 0.12. Remember to divide by the 40,000 first. So we're going to get 0.3 there equals 0.88 to the x. And we can log or natural log both sides. I will go ahead and natural log both sides. 0.3 equals x natural log of 0.88. And then divide both sides by the natural log of 0.88. So we'll, again, always show all of your steps, what you're plugging into your calculator in case if you make a mistake. Show that, then use your calculator. X is approximately, to 3 decimal places, 9.418 years. Okay. All right, another example, it's a little different, is the Jamiesons bought a new house 5 years ago, okay, for $65,000. The house is now worth $117,000. Assuming a steady rate of growth, what was the yearly rate of appreciation? So again, once you see those keywords, you're thinking of y equals ab to the x. Okay, where we have 5 years ago, we've got basically the initial amount is $65,000, and it appraised or appreciated to $117,000 after 5 years. We don't know, we don't know the interest rate. So we're going to put B to the 5 because in 5 years it appreciated to that amount. So be careful, we're not actually solving an exponential equation here because our exponent is not a variable. This is just going to be undoing a 5th power, so we're going to 5th root it. So remember, we still have to divide by this guy. So we're going to take, where's my thing here? Divide by 65,000, both sides. Plug that into our calculator, which gives me 1.8 is equal to b to the 5th. 5th root, or raise it to the 1/5 power. Now be careful, b is equal to, and I'm going to write down a bunch of decimals here, decimal places, 1.12474, and it keeps going on forever. Now, remember b is equal to, since it was appreciating, if you go up to the formula here, b is actually equal to 1 plus r for appreciation, or 1 minus r. So what is my interest rate? This is equal to 1 minus r. So this guy right here is actually my interest rate. R is equal to 0.12474, which means change R to a percentage. R is actually 12.4, oh, I wrote it down wrong, that's a 4, 474%. Okay, the final answer has to be accurate to 3 decimal places. So get used to practicing with your calculator for those. Okay, so the new one, I like to tell my students this is very similar. Just think of this as the one with compounding continuously. Remember we had y, or actually it was a equals PE to the RT. Remember we had e to some interest rate to the t. This is the general formula for growth and decay. When things grow and decay continuously, things in real life, and you can see all of these examples listed out, like populations, bacteria, viruses, radioactive substances, so forth. And think of, temperature is continuous. It doesn't automatically change from one temperature and it jumps up to 10 degrees in a second. It's always continuously growing, and that's why we use AE to the KT, continuous growth or decay. Y is your final amount, A is your initial amount, just like all the others. K is a constant. This is important. So it's not an interest rate, but it's positive for growth, negative for decay. T is also a little different. It doesn't have to be in years. It can be days, hours, weeks, whatever. Okay, so typically when you're reading these problems, if you see, any of these key words, temperature, radioactive substances, bacteria, population, and you see this solve for K, the growth factor or decay factor, or you see K, you're always thinking Y equals AE to the KT. So kind of getting familiar with all of those terms. So let's look at a few examples. For a certain radioactive element, K equals negative 0.377 when it is measured in days. How long will it take 500 grams of the element to reduce to 200? Okay, so we'll have Y equals, actually going to use this. Y equals AE to the KT. Okay, my initial amount is 500. My final amount is 200. I want to know if it's decaying at this rate. This is my my decay constant, which is negative 0.377. And I'm solving for T, which is, in this case, in days. So you go through the same process, divide by 500, okay, which is going to be 0.4 equals e to the negative 0.377t, natural log both sides. You should get really comfortable with this after a while. And we get negative 0.377t and divide. Natural log of 0.4 divided by negative 0.377. When you plug that in, you should get approximately 2.430 days. Always include your units with these. Okay. Now, sometimes we have a two-step problem like in number 4. Bacteria of a certain type can grow from 10 to 350 in 18 hours. So in part A, we're asking find the constant K for this bacteria. Okay, so Y equals AE to the KT. It's growing from 10 to 350. And I need to find K when this happens in 18 hours. Okay. Divide by 10. Oops. Natural log. So K can be found by taking natural log of 35 over 18, which I already plugged into my calculator, is approximately 0.197. Now make sure this is a positive value because it is growth, so you can check your answer. Sometimes people will mix up the initial and the final, and you would get a negative value. And remember, this is growing, so you should have a positive K value. Now, the important thing also, since we're going to be using this value for part B, store this value in your calculator. If you don't know how to do that, work with one another since I'm not there, because you will need to be using that full value or write down multiple decimal places, more than 3, so you can get accuracy to 3 decimal places. Okay, so part B, in how many hours will it take for the bacteria to grow to 1,000? So we go back now, knowing my initial amount, and I want to know, now that I have my K value, It's 0.197. How much time, that's now what I'm looking for, will it take for it to grow from 10 to 1,000? Divide by 10. And natural log. You can go through all the steps. It should be about, and check your calculator please, 23.315 hours. Okay. All right. Last example, half-life. Those of you who have taken biology may have seen some examples of half-life. So problems like this, half-life is basically the amount of time it takes for any substance to decay to half of its size. So you're always going to be using this same general growth and decay formula for half-life. And for in this example, a certain material has a half-life of 15 hours. So all that means is if you start with 64 milligrams, in 15 hours, how much will remain? 32. In another 15 hours, or after 30 hours, you're going to be down to 16. In another 15 hours, or 45 hours, it's going to decrease to half of that amount, which is now 8, and so forth. Now, we want to know how much will remain of the 64 milligrams after 50 hours. Well, you can see it's going to be less than 8, but we want to know exactly how much, right? So we're going to use this formula. Y equals AE to the KT. All right, so how much will remain of 64 milligrams? So first we need to solve for, first step, solve for our K. That just means whatever value I start with, it doesn't matter. I can start with 64, I can start with 100. I just need to know that my half-life is 15 hours. So in 15 hours, the substance will go from 64 to 32. It's going to go to half of its amount. That will allow me to solve for my K, my decay factor. So when I take 32, divide by 64, I'm going to get 0.5. So it doesn't matter what I started with. If I started with 100, this is going to be 50. Start with 200, this is 100. When I divide, I'm still going to get 0.5. Okay. It's equal to E to the 15K. Natural log both sides. So my K is going to be found by plugging in natural log of 0.5 over 15, which I have already calculated. It is approximately negative 0.046, which I have stored in my calculator, right? Okay. Step 2, because that's just solving for the K value. Now I can answer the question, is how much will remain after 50 hours. So I'm going to start with Y equals AE to the KT. Now I know my K value. I want to know, starting with 64, how much is going to remain? Well, I'm going to use my stored K value and plug in 50 hours. So there's no solving an exponential equation. You literally just plug this value in to solve for Y, right? Which, again, practice on your calculator. Make sure you're getting these correct values. I got 6.349 milligrams. Okay. I hope that helped you. Make sure you have your note sheet completely filled out to help you with your homework, and this will be posted on the calendar as well. Good luck, you guys.